each other's grades without permission, so it gets awkward. So I've got to ask. So Mr. Ward, are you okay if people know your grade?
Yes.
Oh, okay. Good, good. And we're going to use his to review. Nice job, Mr. Ward. I already gave you one?
Well, you gave me.
Oh, wait. Very good. Go heat it up with a friend. Nice. Hey, that'll save me one. I did start my diet Sunday, so for real, I did. I am starving to death.
Next Sunday?
So no, this Sunday. I woke up. I was 2:23 after I stayed up till 2 a.m. eating pizza, watching the Tigers lose.
Oh.
So I was like, okay, diet starts tomorrow. So anyway, so we're starving ourselves to get down to about 2:10. Oh yeah, Mr. Blosner, you okay with everybody knowing your grade? Very nice. Blosser, sorry. Blosser. I did it, yeah. Blosser, okay. And let's see. Thank you. I actually like the ring of that. I like that. Isaiah, you good with it?
Yeah.
Okay. And Clayton. Woo. You okay? Everybody knows your grade? All right. Well, you didn't get 100. That was my joke of the day. But actually, I'm still gonna give you an ice cream. I'm still gonna give you an ice cream because you used your joke. So enjoy.
Hey, he got his ice cream. Hey, that's not better.
He only missed one question, and he typically has one of the highest grades in the class. So with all that said, a little good job, Clayton. The one he missed was, if you have yours open, we're going to go from reverse to the beginning, was the very last question here. Drag and drop. I briefly touched on this, but when I was grading your exams, I realized, oh, you know what, I did not cover this as in-depth as maybe I should have for an exam question. We will cover it more in airframe, which is why I kind of danced around the corner of it. But DC generator in the last part. But a DC generator, the field is typically the stator. So back to on a generator, normally the rotating part is where we harvest the energy. So the rotating part would be the rotor on what we call a DC generator. But in an alternator, diodes are what convert the AC to DC voltage. Where in that DC one, because the stator's rotating, making AC voltage, it's the commutator that converts the AC voltage to DC voltage. And this is the part that I didn't cover that much. An alternator, actually he's got them backwards is the problem. So a generator typically does not produce as much amperage at low RPM as an alternator does. When you turn on your aircraft that's got an alternator, we always say, go ahead, turn the alternator circuit breaker on too, because even like just the starting, and if the thing hiccups a couple times, alternators do a pretty good job of making amperage. Now there's a big discussion on should you turn the alternator on before it starts, because if it's making amperage, that means it's kind of taking work from the engine. So it's making it slightly harder to start, but not that much. But if you have an aircraft with an alternator, even at idle, a low idle, it'll make a good 20, 30 amps. Where a generator, if you're at idle, not so good. Part of the reason is what we're spinning inside our generators are a little bit smaller rotors, right? I think I put them away. But the rotor in a generator, it's a little bit smaller on the inside, so at a lower speed and everything, it's just not doing as much. Where with our alternators, we're spinning the magnet and we're still cutting all those flux lines. They just work better. Old aircraft, people that were flying IFR would get themselves in trouble because their amp draw would be so low when they're just idling around getting ready to take off that they're draining their battery, draining battery. And they didn't start recharging the battery until you got up to full power. And then, whoa, now we're recharging. So IFR flights, especially if you were sitting there idling for too long with a generator, you could actually drain your battery down, which isn't great. So that's the end that Clayton reversed. Not so much bad on his part, so we give him a nice round. So we're gonna work our way backwards through this exam. Use the image below to choose the correct answer. answer, device in an aircraft consumes 26 amps, so the wire feeding it needs to have a 30 amp breaker. The wire is run in a bundle. What does this chart tell about our wire size? And I gave a little bit of extra information than you probably need, but 26 amps, so we need a 30 amp breaker. So if we got a breaker, we would come down to 30 amps. Oh, this is the one where it's a little tricky. Make sure we're the right one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Yep. So we would need at least a 12 gauge or larger wire is what it's saying. It does give you a bunch of extra in the bottom here that talks about wire bundles of 15 or more wires with wire carrying capacity not more than 20% total carrying capacity in the bundle as given. If you were going to run it not in a bundle, you could like get to where in an airframe, we talk about it more, we could like, well, you know, we can cheat by 10% or 20% because it's not in a bundle, and you can cheat a little bit. So that's actually on the exam why I put it's in a bundle, is if you really wanted to split hairs and you were the aircraft designer, we can start cheating a little, but I didn't want to get way off in the weeds for this question and be like, look, we could have done a 14 gauge and you have show me 15 charts that you memorized. And I'm like, yeah, we'll make it simple. This chart, it's a bundle. So that's how that chart works. Get familiar with it. An airframe will do it a lot more. Is whatever size breaker, that's the maximum size that you can run for that size. Stop me if you need questions somewhere. Oh, I used the chart below. This was a little bit tricky, so I had the paper ones. But 28 volt system. Wow, hard to read on this screen. 35 foot long, 10 amps. I can't read it at all. If you went down to your chart or your computer where it's not too bad. So what ended up happening is we were just past the line here, so then I drop it down. That's going to be up to my 12, I do believe, if I'm looking at that right. Does that sound right? Okay. That's 45. 44. Somebody said I should throw a third one in here just to mess with you. This was supposed to be a gimme answer. We covered the wire fitting out in the slot is where it counts. So that would be a 4 gauge. That is not how it's designed. I don't know why they design those things that way. It's kind of silly. But make sure you're saying it's the dimension between the slot is how you're measuring. And remember, it's a solid wire, solid copper wire. Comments, questions on that one? Okay. All right. Stranded copper wire is 19 individual conductors measuring 14.3 thousandths of an inch each. So we would go down to our 14.3, get our circular mills, which is 202. So we do 202 times 19 gives us 3,838. 3,800, ooh, it puts us kind of in between this 14 and 15 gauge, and we go, oh man, did we measure wrong? How does that work? But I think I purposely didn't give you a 15 gauge, right? So if you were like hemming and hawing, I can't figure out which one it is. The only one in the neighborhood is 14 gauge, so I tried to make it a little easier for you. Yeah.
So for the use of this chart, you typically just go with the bigger the gauge, right?
Yeah. Actually, let me back that off. I'd probably go with the smaller gauge because you don't want to say the wire's bigger than it actually is. So, bigger number, but smaller gauge. It should work out perfectly. So there's a calculation error, and that's where I go if you're not sure, err on, you know what, let's run a little bit bigger wire, because that's why you'd be asking it. But that goes back to kind of a similar question of why would you be doing this? There's not really a good reason other than to just pass the test. You're going to go to the IPC, you're going to go to what's labeled on the wire, you might even call the manufacturer, say what size wire is that supposed to be. So this is more of a get you in the neighborhood so you understand the concept. Mr. Marsh.
Can you explain how you got to that?
Yep, I can do that. So thousandths, or that's what that says. So we go to our page, there we go, to where the diameter in mils are thousandths of an inch. So 14.2 is basically the individual strand we measured. So every individual strand is a 27 gauge. So then we go over to the circular mils. So what they're saying is a 27 gauge wire has 202, if you're going to do the area, but 202 round 1,000th of an inch circles would fit, obviously overlap. And that's what we base our gauge on, is the wire's circular mils. So then we're going to take that 202, multiply it by the 19 strands that we said we had. So 202 times 19 gives us 3,838 if we do the math like that. So we're just going to go up our circular mils and say, which one is it? 3,800 and something. So we're in between those two, but we're pretty close to our 14 gauge there. So we're going to say, well, we probably messed up just a fuzz with that. And if we go back, I said it was 14.3, if I'm not mistaken, right? Yep, I did. So notice this one's 14.2, so you're actually, you'd say it's slightly bigger than 202, which gives us, right on the money, slightly bigger than 3,800. So, cool. I don't know why, but I like those questions. Maybe I just like that chart. All right. This one was just matching components. I'm just going to say, any questions on that one of the ones we asked? Okay. Keep going. 41. Who many, I gotta fix that. Who many millivolts are in 1 volt? How many millivolts are in 1 volt? So that'd be 1,000. 1,000 millivolts in 1 volt. Which of the following best describes the operational principle of nickel cadmium? Alright, so this one, I'll admit, it's a little bit tricky, but let's look at the incorrect answers. At full charge, the electrolyte will be at its lowest level. No, at full charge, it's at its, well, close to highest level. There's a little bit of gassing, so there's like the star saying highest level. So this one's not right. When positive plates slowly give up oxygen, which is regained by the negative plates, the battery is charging. I'm like, oh, that could be, I don't remember chemistry exactly how that works. Turns out that's actually backwards, but I'm not sure. So then on this one I go to completely charged nickel cadmium battery. Some gassing must take place, thus water will be used. This is the correct answer if you were studying prepware or whatnot. So this is backwards. So the positive plates, I believe it's gain oxygen in a nickel cadmium. It's kind of reverse with the oxygen going on of what a lead acid battery would be when we say oxidizing. So if you really want to know the chemistry, that's why nickel cadmium's kind of reverse, and we got different chemicals going on. But yeah, that's the right one. I actually partially threw that in because I knew we were going to be doing this review, and this one comes up on writtens and exams, and the FAA really likes that comment. So like, well, one more opportunity to review it one more time so everybody gets it cemented in. 39, what is the likely result of anything of servicing and charging nickel cadmium? They both bad. It's not like only one battery goes bad. Both batteries are going to have problems because the gases will mix or chemicals mix, and we don't like that. So don't charge them in the same room. Alright, how can you charge batteries together? Number one, I just say don't do it. But the only one that's not true is number 3. Batteries of the same voltage and same amp hour capacity must be connected in series with each other across the charger and charged using the constant current. No, we can, if they're the same capacity and amp hour, even better, just put them in parallel on a parallel charger and let them charge up. So the other two are true. they're different voltages but similar capacities, you put them in series. If they're different capacities but same voltage, you put them in parallel. Okay, our lead acid battery with 12 cells, no load. So 2.1 times 12 we'd have to do to get, hey, what's our starting voltage on this battery? 2.1 times 12 is 25.2. So our starting voltage would be 25.2 volts. Furnishes 10 amps to a load of 2 ohms resistance. The internal resistance of the battery in this instance is, oh, they gave you all the math on here. So we start with 25.2, 10 amps with a 2 ohm load means we're doing 20 volts. And if we want to do our triangle, once it's running, it's saying 2 ohms, 10 amps, 20 volts. So running our battery is 20 volts. That's a big drop. It's not ideal. We're probably not going to have that. So basically our battery has 5.2 voltage drop, and then we can put that in the triangle. 5.2 and 10 amps. 5.2 divided by 10. 0.5, is that, okay, make sure I'm going the right way. So 0.52 ohms, yeah. Thanks. So that's how we do those ones, as a reminder. Okay. Kind of a weird one you probably will never have to do, but the FAA likes that one as well. Alright, this one, I figured I had to do some sort of logic gate, so I picked one of the easier logic gates and tried to give it to you that way. So, an OR is the one that if either OR get an input, we send it out the backside, right? Because it's an OR. But we said I got an exclusive OR, an exclusive NOR, which is an OR with an X and a not and. So, exclusive OR is that one. Exclusive with a dot, NOR, and oops, flat on the back. Not and. So which of the following logic gates will provide an active high out only when all inputs are different? So if we put a 1 and a 1 in each of these, we'll just work through. A 1 and a 1 and an and, well, we like and gates, so that would give us a 1. Oh, except it got a reverse. So we go, well, that one wouldn't work. So which of the following will provide an active high only when all outputs are different? So it doesn't give me the active high on that one. The next one down, if we got an OR gate, 1 and a 1, I've got either OR, which would give me a 1, but then it says not, which gives me a 0. So that one wouldn't work. So then we get the exclusive OR. Hey, I've got one or the other. Uh-oh, exclusive OR. Let's see, do I got that right? Did I do that wrong? Exclusive OR.
That's it.
1 and 1. Because exclusive would be 0. Yeah. So I got all zeros. I didn't get my active high yet, did I? So then I got to go back.
Only when all inputs are different.
Yeah. So if I go 1 and 0, that's why we're reviewing. 1 and 0. This one would have tripped me up. Now, on an and, they're not both of them, right? So I would get a 0 and a 1. Oh. But they're not different. So let's go all the way this way. So that's the second question, right? Yeah. All inputs are different. Go to that one. All right. Which is fine then? Active high only when all inputs. Sorry, I do want a 1 and a 0, don't I? 1 and 0, 1 and 0. This was easier when I wrote the exam, not in front of 30 people. So my AND gate, 1 and 0, but they're not different, so it doesn't. Only only when all, that's what it was. So I don't have, there. 1 and a 0 would have given me not an and, so it'd be a 0, but it gets reversed and it's a 1. Alright, so that one eliminates that guy, right? Because I don't have all my inputs different, so that can't be the right answer. Alright, a 1 and a 0 on this one. I have a 1, so it would give me a 1, and it'd be reversed to a 0. So that one's good, but on this guy, if we, my brain's coming back, if we had 2 zeros, it would say 0, and then reverse it, say not, and give me an active high. That's why that one can't be our right answer, because if I have 2 zeros, 2 similar inputs, I get a 1. So this is the reason that one won't be correct, and this one will be correct. Wow, I really stumbled through that. That was a long question. So whoever got that right, it took me a little while too. Okay.
Why, I guess why is the NAND wrong?
Well, this one?
Yeah.
So, this situation right here. So, let me erase this part. It says which one will give us a 1 or active high only when all inputs are different. So right now I got a 1 and a 0, so the inputs aren't different. And an and originally with a 1 and a 0 would have produced a 0, but it gets reversed because of the not, so it gives me a 1. So it won't give it to me only when they're different. It'll give me an active high. Okay, so it gives me an active high. Wait a second. Which of the following logic gates will provide an active high only when all inputs are different? So on this and, if I do a 1 and a 1, what does it give me? 0. Wait, is there not? 1 and 1 would be a 1, 0. Okay, what if I do 2 zeros? That's why. The not and. Alright, so that gives me an active high, but I have the same on the input. I need to take a break. That's why. Sorry. That's what, that one right there separates the 97s from the 100s. I can do that. Alright. Which one's correct for the XOR gate? And I think you picked number 2 is correct on there. Exclusive OR. So this one, yeah, we'll just stick with it's number 2. That one is correct. So they're exclusive. I do have one that'll flow through. This one, it's exclusive, so it wouldn't pass it through. And this one's just incorrect. We do have one that's exclusive. It should have been a 1. So number 2 is the correct one. All right. 34. Zener diodes are typically used for voltage regulators. That is true. Not full wave rectifiers, because a Zener diode, if you're using it as a diode the wrong way, A wouldn't use a Zener, but B, it would just be a half wave rectifier. And with that, we don't typically use a Zener for that. We're just going to use a regular diode for that. So voltage regulator is what the FAA likes you to know. We use Zener diodes for it. In an NPN transistor application, solid state device is turned on when the, so if we were going to just draw it out, say NPN, that would mean my base has to be more positive than if our emitter's out here, than my emitter, but the base is the key, so it's when the base is positive in respect to the emitter, and then NPN. So, reminder of that, whatever the middle number is, whatever the base is, because it's the middle number, has to be more of that than the emitter to make the thing work. 32. Picture. Troubleshooting an open circuit with a voltmeter as shown will, and notice we have a break in the line here. gonna show voltage, cause all the pressure is gonna be stacked up, whether you wanna go positive or negative. It's gonna be stacked up across that load, the resistor trying to get through the load. But it can't get through the load, so we're gonna show voltage there. Okay? 31. What is the purpose of the ground system used? We don't show the source of electrical energy. That's kind of like, ooh, that's close. Because if you think electron theory, then that's a dirty question, isn't it? But we don't work in electron theory. So, to show that there's a return path for the current between the source of the electrical energy and the load. We don't like to say that there's a common bus for connection to the source back to, we usually say a plus is the source because we think in conventional unless otherwise stated. How many of you guys were like trying to think of it? Anybody? Good, I've got you trained. I've got you indoctrinated. Now some of you are going to be like, wait a minute, that's a bad question. Okay. So let your mind wrap around that one for a little bit. Wait a minute, if we're electron theory, that means that I actually have positive voltage, not positive, negative voltage. I have my electrons connected to my loads all the time. All we gotta do is give my electrons a return path to the battery, and it would run. So, anyway, that's kind of a funny logic, but it works, because you can think of it either direction. So, the reason I bring that up, and I take a little time with the exam, is we always gotta think of electricity in a circuit, right? A complete circuit. You don't think of it as just positive voltage or just negative. And that's why when we get into airframe, sometimes we'll put the switch and cut the power or the electron flow into a load. Sometimes we'll cut the flow out of the load. It doesn't really matter, as long as you're interrupting the circuit. All right, when referring to an electrical circuit diagram, what point is to be considered zero voltage? And that's back to the same kind of question. The ground reference, they typically consider zero voltage.
How about an alternating?
Alternating current, that's part of why we consider ground reference zero voltage. That's actually it. So if you have alternating current and you got a ground, the ground is typically the zero in the middle of it. So even more specifically, it's because in alternating current, ground is typically zero. So in DC, we still consider that there's ground. Did I draw it that way? Yeah. We'd still consider that zero in a 12-volt system. It's just a steady 12 volts up. So if you're like, do I have voltage at my, you say, okay, reference to ground, do I have it? That's why that word reference is in there, ground reference. All right, so somebody said, is this a trick question? It seems too easy. The image below shows the landing gear, and is it up, down, or transitioning? We go, well, switch is shown, gear down on the ground, so down. So that should be a fairly easy answer for you. Whenever you're looking at those diagrams, make sure you read them first and see if it tells you. A thermal switch or thermal protector is used in an electric motor, is designed to, and it's open the circuit in order to allow cooling of the motor. We wouldn't want it to reroute to ground, that'd be bad. And they might have switches that do this, but we're gonna call those more like thermostats. We're not just gonna call it the thermal protector. Thermal protector is, man, we're too hot, shut this thing off. 27, we're getting there. Most of the early ones go quick. What is correct concerning a parallel circuit? And that's just back to, we got a bunch of resistors in parallel, right? So the total resistance of the circuit will be smaller than the smallest resistor. So that one we should all have memorized pretty good. And I'm betting this one, oh, wrong question. Through which material will magnetic lines of flux, lines of force, same thing, pass most readily? I think I even tweaked this just to make everybody happy. So they most readily So much so that the iron says, come over here, come through me.
I didn't think about it. Iron eyes. But
Alright, this one must be asking us to do some math. So, we'll whip it out, kind of. I've got 10 and 5, so I know the total resistance is gonna be, at least 15. This whole section here is gonna get simplified if you do all the math. Well, it's gotta be less than that number, so, I know it's gotta be less than 19 ohms. I'm not even gonna do the math. Go with 17. You did all the math. I tried to teach you. Alright, you can do all the math you want, but everybody see how I did that? Yep, multiple choice, just give it a quick glance. And that's in the reality of, as we're going in electricity, that's the idea we want you to get. Nobody's ever gonna ask you to calculate the total resistance of the light bulbs in your aircraft. They're gonna say, you added 2 more lights, what happens with the amperage? Well, the amperage goes up because the resistance of that total circuit went down. So, added 2 more lights in parallel, right? So, I like reviewing that one. Electrical resistance. Well, this one's tricky. But if you draw it out, not so tricky. So, I got 3 light bulbs, or whatever they are, in parallel. Which is true? If one of the 3 light bulbs is removed, the total resistance of the circuit will become greater. So back to, let's say it's 2 ohms, 2 ohms, and 2 ohms. I'm gonna make it easy on me, sorry. 3, 3, and 3. Total resistance of this right now would be 1 ohm, right? But if I remove one of these guys, now my total resistance is 1.5 ohms. The other way to think of it is, if I just keep adding light bulbs, if I keep adding light bulbs, my amperage is gonna go up, 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 because I'm just adding more light bulbs that are all gonna be running on the same voltage. So more amperage is less resistance, so that's the correct answer. The other 2 are just incorrect statements. 2 electrical devices will have the same combined resistance if they are connected in series as parallel. That's not true. Because when we put them in series, they add. And an electrical device that has a high resistance will use more power than one with a low resistance. That's opposite sides of that. I think what I did on this one was I was trying to keep your exam shorter for me, but not giving you too easy, so I put 3 true or false ones all in one question. It's tricky. It's almost, it's like asking you to answer 3 true or false all at once. If each cell connected in series equals 2 volts, how would a 12-cell lead acid battery be rated? So that's just back to saying we connect our cells in series, they're 2 volts each. 12 cells gives us 24 volts. So that was supposed to be just a quick math one for you. The total current between C and D, this tripped a couple people up. So between C and D is this wire here. So I want to know the total current going through that wire. So all the current that goes through that one is going to be the amps that come down this road. So it's all the amps that go down that road and all the amps that go down that road, right? So you got to figure out where we're at. This thing's drawn a little funny. If you wanted to, you could redraw it to just be that, right? It's the same thing, it's just how they took them off. So if we had 24 volts, 24 volts divided by 40 is 0.6, so this one would have 0.6 amps. 24 divided by 10 is going to be 2.4. Trying to be smart like geese and just be able to do division with zeros. Yeah, right?
No.
No?
I just put in my calculator.
Oh. It is 2.4. Oh, some of you guys are sharp. You're like, you're dividing by 10, this should be easy. I'm like, yeah, but I'm in front of like 29 people up here. Alright, so 2.4 plus 0.6 is 3 amps have to go down there, right? So answer should be 3 amps. Did we get right? Yes. Okay. Erase that. 3 resistors, oh boy. I have to draw that real quick. 3 ohms, 5 ohms, 22 ohms are connected in series. So 3, 5, 22 in a 28 volt circuit. How much current will flow through the 3 ohm resistor? Making you draw it, making sure you don't just try to do it in your head and think it's a parallel, right? So we go, well, the whole current in the whole system, right? So we gotta add these up. 22 plus 5 is 27, 28, 29, 30. So my RT would be 30. So then we got 28 volts divided by 30 ohms, 9.3 repeated. Uh-oh. 0.9, I put the decimal in the wrong spot. 0.93 repeated. Now that I messed it up, I better draw it, right? 28 divided by 30, and you plug that in your calculator, 0.93. There we go. Okay. Question 20. Transfer without electrical connections is the big key here. So how do we get power from one thing to another thing without electrical connections? And that's induction. Capacitance doesn't really transfer any electrical energy. That just stores and discharges, so that wouldn't count. Can cause excessive arcing and heat, and as a result is practical for use only with low voltage. Well, I think that one got thrown in there. What are we talking, like making electricity jump through a gap? Yeah, that would. And if that was what you were talking, it wouldn't work with low voltages. So that was just thrown into the, make sure you understand what's going on. So induction, so your transformers transfer power without touching anything. Oops. We're getting there. Which of the following are commonly used as a rectifier in electrical circuits? And that's diodes. They cut off the bottom as a half-wave rectifier, or if you wire 4 of them, you've got a full wave.
Especially the transformers, the coils that are wrapped around a shared bar.
Okay.
The coils don't touch the bar, do they?
Nope, they're insulated from it, yeah. Sometimes the wires, and even on motors, it might look like they're touching. And when we get into airframe, we'll talk more about it, but the wires actually have a varnish on them, it's an insulation. So even though it looks copper colored, the electricity won't ever go from wire to wire. If it went from wire to wire, it would make no sense to have a bunch of coils, because it just go through and come out. So anytime you see a coil, even if it looks like it's just a copper wire wrapped around, it is insulated from everything. There's a copper varnish, there's not copper varnish, there's a varnish to keep the copper from touching each other. That threw me off for years when I was working on motors. I'm like, how do they not just short through? Oh, they've got this fancy, I use the word paint, but they got a fancy paint that insulates them. What unit is used to express electrical power? So the watt is power. Remember, voltage is pressure, not necessarily the amount of power. And an amp is current. A 12-volt source is required to furnish 48 watts to a parallel circuit consisting of 2 resistors of equal value. What is the value of each? Ooh, that's a tricky one. So 48 watts, parallel circuit, 2 resistors of equal value, 24 volts, I should say, 24 volt. So how many amps do we need to get 48 watts out of 24 volts? 2, right? So if we're going to draw our watt triangle, 48 watts, it's going to be volts times amps. So amps, 24, I could have done it the other way around. 48 divided by 24 is 2. So we know we got 2 amps on our system. So So that gives us a total resistance of, that would be 24 divided by 2. It's going to be 12 ohms. So RT would be 12. And since we have 2 of them, that's going to be, well, 24 and 24. It's going to split us down to 12 for a total RT. Everybody following me there? Okay. And 16. Cabin entry light of 10 watts and a dome light of 20 watts are connected in parallel to a 30-volt source. If the voltage across the 10-watt light is measured, it will be, well, we're in parallel, right? So we already told you that it's just going to be 30 volts. Equal to the voltage across 20 watt. We're in parallel. So, no tricks there. Which term means 1,000th of an amp? That's with the .001. It's 1,000th, so it's a milliamp. Okay, 14. We can do this. We can get there. For resistor 5 is disconnected at the junction R3 and 4. So basically they're saying, yup, this is open. That's an open winding. What will the ohm meter read? Now it doesn't matter if you put the ohm meter over here or over here. We're just looking for resistance total, the way that's connected, right? So basically what we got left is we've got a 12, a 6, and this now is in series. So that would be a 10 if we were going to redraw that. 6 and, oh, sorry, 12, thanks. 12, 6, and 12, so we could do all the crazy math, or we could be lazy like Case and be like, oh, let's turn that into 2 12s. So we'll just add one more 12, because that'd be basically the same thing, and then I can just do 12 divided by 4 is going to give me 3. Otherwise, you could do the 1 over 12 plus 1 over 6 plus 1 over 12 equals 1 over RT. Everybody good with that, how we got there? Okay. This one kind of tripped somebody up. I gave you X of L and X of C, right? Because I said we have a reactance of 10 ohms and a reactance of 4 ohms. So I gave you the X of L and X of C. So basically we just had to plug in our formula. We need to know Z. We put 8 here. 10. Is that the 10? Yeah. And 4. So 10 minus 4 was 6 squared. So it was 8 squared plus 6 squared, and the square root of that. The answer falls out to be 10 ohms. Okay. How much power is being furnished to the circuit? So 23 amps, 5 ohms, that's our voltage source. So if I said I got 23 amps, 5 ohms, we'd have to figure out how much voltage we had first. 23 times 5 is 115 volts, but they wanted power. Power's in watts, so we got to take our 115 times 23 to give us our watts. And that gives us 2,645 watts. Okay. 24 volt source is required to furnish 48 watts to a parallel circuit consisting of 4 resistors of equal value. What is the voltage drop across each resistor? Is it parallel again? That makes it easy. 24 volts in parallel, each one gets 24 volts. Alright. 10. The potential difference between 2 conductors which are insulated from each other is measured in. Potential difference, another word for that is voltage or pressure difference. So volts is the right answer. This one, they have you do all the math. We've done it a bunch. Does anybody want me to do the math? Okay. Shane answered for the group. When inductors are connected in series in a circuit, the total inductance, if they're in series, is going to be added to each other. The total inductance, and remember inductance is resistance to electrical flow, or changes in electrical flow, I should say. When different capacitors are connected in parallel, they add up. It's like stacking Legos. We like doing parallel. Capacitors like parallel. 6. The total capacitance of a circuit contains 3 capacitors in parallel. They stack up. So we got 0.02, 0.05, and 0.1. Just going to add those 3 numbers together then to give us 0.17. And the amount of electricity a capacitor can store is directly proportional, which means if it goes up, the other goes up. So directly proportional to the plate area. Yep, if plate area goes up, the capacitance goes up, and inversely proportional to the distance between plates. So if the distance between plates goes up, I can't store as much. We know that's not true because the plate area. So that's why that one's correct. And when different rated capacitors are connected in series in a circuit, the total capacitance is, and I gave you the formula just to, help, but you should be able to know capacitors in series, it's going to basically really be a bad thing. We don't like that. They're not going to add up. We got to go with this bad thing. So it's less than the capacitance of the lowest rated. Electrostatic fields are also known as dielectric fields. That's correct. Reviewed that one several times before the exam. And the term that describes the combined resistance forces in the AC circuit is impedance, measured in ohms. Finally made it in reverse order to number 1. The working voltage of a capacitor in an AC circuit should be at least 50% greater than the highest applied voltage. Yep. We don't want it to burn up. All right. A little bit boring today to start a Monday, but we did it. If you need to retake it, we'll clear this off and we'll get you set up in the library to start it in, let's say, 10 minutes, unless you tell me you don't want to do it then. So at 8:10, we'll get you set up. All right, other questions? For Rich, maybe. Go for it. Okay. Anytime you give somebody the pulpit, you gotta be careful.
Yeah, so last week we were talking about the written. Who was able to schedule their written on PSI? A little over half. Anyone who hasn't, try to get it done this week, because the slots will fill up and there's other people outside of school that are doing it. Did anyone schedule it before the 13th of November? No? Okay, good. Because it was an option, but Barb was saying that she wants us to give it at least a week before.
Also, I found it doesn't work on Chrome, so you might have to use Safari or Firefox.
Right.
Okay.
Yeah, anyone who hasn't scheduled it, try to get it done this week. Help you go.
Thanks.
Thanks, Jared.
Thank you for the public service announcement. All right. Anything else for me?